Hi, everyone. I'm Diane Wen, and I am a software architect at Linus Health. I'm also acting as the interim tech lead of our integration team. And today I'm going to be talking about our use cases for Temporal and why we think it can play a critical role as our new workflow engine. So I'm just going to keep this very high level. I'll start with a brief summary as to why orchestration is so important within our platform. And then I'll talk about the gaps in our current workflow architecture and where Temporal can help close those gaps, as well as what we concluded from our POCs against Temporal. And then finally, what our next plans are for implementing Temporal within our organization. So just to give you a bit of background on our company, Linus Health is a digital health company focused on transforming brain health for people across the world. So we offer a digital cognitive assessment platform that supports early detection and intervention of cognitive and brain disorders, including Alzheimer's disease and other dementias. We currently support 2 market verticals, one being life sciences and research customers, as well as healthcare delivery and primary care customers. Our core products are mobile and web-based, where cognitive assessments are taken on an iPad, and assessment results and recommendations are displayed in our web applications and integrated electronic health record systems. So like I just said, one of our core products is iPad-based, which is used to quickly administer sensitive cognitive assessments. And one of the more common assessment workflows we offer to our customers is called the core cognitive evaluation, which is comprised of 2 subcomponents, one being the digital clock and recall, and then the other being the life and health questionnaire. So as a patient completes these cognitive assessments, the raw metrics from their tests are scored and analyzed by our processing pipeline, and then the process results are displayed in our consuming applications, so research-oriented applications, clinical applications, and then also our integration applications that sit between the Linus platform and electronic health records, or EHRs. So to break down this particular product workflow even further, the provider assigns a set of tests called a core cognitive evaluation, or CCE for short, to a patient and then gives them the iPad to take those tests on. The CCE is further broken down into the DCR, which is short for digital clock and recall, and LHQ, which is short for life and health questionnaire. The DCR is further split into multiple smaller test segments, including a clock drawing, immediate recall, another flavor of clock drawing, and delayed recall. And all of these segments rely on the sensors of the Apple Pencil and the iPad's audio recognition. So at a high level, the patient is expected to copy and draw a clock when prompted, and then also repeat some phrases. And after the DCR is complete, the patient will complete the LHQ, which is a 32-question survey. So each component here that comprises the core cognitive evaluation, or CCE, it has its own analysis engine, and these engines live within our custom-built processing pipeline. Once the metrics are analyzed and the results are saved, downstream product workflows have to be notified so that our consuming applications can start rendering the results. And while this is happening, the provider is waiting for those results to become available. And once the consuming applications workflows are complete, that is when the provider can view the test results for that patient. So there are multiple engines that live within our homegrown processing pipeline that handle the more discrete components, like the clock drawing, recall, LHQ, as well as the analysis and interpretation of that data. There is a hierarchical order to how these tests are structured. So these yellow boxes are known internally to us as segments. The DCR is categorized internally as an assessment, which is a grouping of segments. And then the CCE is categorized internally as a battery, which is a grouping of assessments or assessments and particular segments. The orchestration of the segment engines and how they feed into the higher order assessments and batteries is stitched together by a bunch of distributed Lambda functions and a pub sub pattern, so tightly coupled SQS queues and SNS topics, all while using Postgres on RDS as the backend. However, the workflow orchestration itself, in reality, looks like a bunch of spaghetti because of how many different things we have to keep track of on top of all the circular dependencies. And because it's a lot of spaghetti, there are a bunch of architectural and operational issues that stem from it. So this processing pipeline that I just mentioned was built over time as needed by individual engineering teams, with little concern paid to consistency or standards. And as Linus Health grew their business, so did the product features dependent on this pipeline. Debugging became a very time-consuming process due to lack of workflow visibility. Timeouts were becoming more difficult to manage in an asynchronous world. So a concrete example here would be whenever a customer logs into one of our portals and wanted to click a button to manually download a report containing a patient's results, occasionally it would fail due to maybe some networking issues. So then the customer had to click the same button again and wait for the report generation workflow to retry. And then if that timed out, they would have to wait an additional 3 minutes and retry again. So obviously this lends itself to very poor end user experience. There was also a significant lack of retry logic and error handling within this workflow, resulting in a large amount of manual involvement from our engineers, which was exacerbated by the lack of workflow visibility. So most of the time, we had to find engineers with enough tribal knowledge to help troubleshoot. There was also not really a concept of a run or attempt in a workflow. There did not seem to be a source of truth for messages and event shapes, which made testing our workflows very difficult. There were many subscribers to the workflow's emitted events, so the addition of new events often results in unpredictable side effects. We also had to worry about versioning from both a deployment perspective and also business perspective. So whenever we deployed new analytics engines, we had to make sure in-progress workflows could still successfully complete. We also had to version pin or freeze our engines/algorithms for our research and pharma customers who had contracts that spanned multiple years. So it was extremely tedious to maintain that, especially as we continue to grow our two market verticals, so research versus clinical. So for both of these cases, engineers cautiously avoided making significant changes due to this constraint. We also had an open question as to how we were going to solve for scale in a customer organization or a particular market vertical and still fairly distribute processing work within our architecture. So at this point, we started looking into alternatives to our homegrown solution. Step functions was a possibility, but it requires too much logic baked into the runtime, and it still did not provide enough visibility into where things went wrong within a workflow. Cadence was also a very attractive solution because it supported fault-oblivious stateful workflows, but it did not support all the languages used by our engineering teams. It only offered a Go and Java SDK at the time we were looking at it. We then realized that Temporal is a fork of Cadence and provided both a TypeScript SDK and a Python SDK. Our product engineering teams at Linus Health use TypeScript, and our analytics teams use Python. The concept of workflow as code was extremely appealing to us. Temporal also seemed to provide more robust support for error handling and automatic retries of workflows. And because workflow is defined as code, there seemed to be a lot of flexibility with enforcing the order of things, which is critical to how we hierarchically group our engines and assessments and batteries. Traceability and testability of workflows was also another attractive feature for us. And then versioning of workflows and workers was also another plus. So at this point, Temporal looked pretty good to us, but we wanted to do a POC to assess the feasibility of using Temporal at Linus by basically mocking our core cognitive evaluation battery workflow against Temporal. So we created very basic representations of the workflows and activities that were required and had this running locally against the Temporal Docker Compose files. So we had local worker servers executing the POC workflow against a locally running Temporal cluster. We also took some Docker images provided by Temporal to create container task definitions on ECS Fargate. And as a side note, we knew that Temporal offered readily available Helm charts, but we are not a Kubernetes shop, and we're trying to stay on Amazon's ECS service for as long as possible. So given the hierarchical order of our engines, we designed our workflows based on that. So we had separate workflows for battery result processing, assessment result processing, and segment result processing. And then each component that represented an engine or a functional unit became an activity. We also established parent-child relationships between these workflows, with the parent workflow being the battery workflow, and then the assessment and segment workflows being child workflows. The general idea here is to map the logic from our previous Lambda functions into activities and still continue to maintain an event-driven architecture by having our workflows listen for signals. So when a battery workflow is triggered for a given patient, a signal will be sent to the assessment workflow, and then while that workflow is running, the assessment workflow will also send a signal to the child segment workflow. The segment workflow is responsible for orchestrating the activities that represent our analytics engines. So think clock drawing, recall, et cetera, as well as uploading those results. And once the results are ready, it will traverse back up to the assessment and battery workflows, and then a notification will be published saying that the results have been generated. The main reason we are structuring our parent-child workflows like this is because the assessment workflows and the segment workflows are meant to act as separate services that can be invoked by other workflows. This is the original concept we had when we first started building our V1 processing pipeline. We also started ideating on what it would look like if we were to implement Temporal as our main workflow engine and thought about re-architecting our downstream workflows against Temporal as well. So during post-processing, one of our other important workflows that's core to our business falls within the integration space, which I'll get to in the next slide. So like I just said, another important workflow to our business is related to integrations, and it happens in post-processing. And this particular integration that I'm about to describe is concerned with uploading Linus assessment results for a patient to the patient's medical chart in the customer's electronic health record or EHR system. So the idea here is when a patient shows up for their appointment in the clinic, the provider will place a clinical order in their chart for that patient to take a Linus test. And this order serves as an event trigger that we can use to automatically import or map the patient in the customer's platform into Linus. And after the Linus representation of that patient is confirmed, the battery workflow and the processing pipeline is triggered. And then once complete, our integration workflow uploads those test results to the EHR. So here we also use the concept of parent-child workflows and also activities representing functional units when thinking about what this order workflow would look like against Temporal. One of the EHRs that we integrate with does not support conventional event publishing. So literally the only way to get notified of these incoming clinical orders is to continuously pull a data feed that's owned by the vendor. And once we pick up a new order, we can start using contextual information from that order event to get the patient from the vendor. So the first step in that child workflow is to import the patient from the EHR, which involves getting the patient profile information from that EHR and then importing them into Linus if they did not previously exist. The second step is to assign a core cognitive evaluation to that patient. So going back to like the term battery, when we assign any sort of battery, which also includes the CCE, we have to know who to assign it to, so the patient, and then also who will be the one to interpret the results, so their medical provider. The interpreter is a provider at our customer who will have a corresponding Linus user in our platform. So that means that within the context that we get from the original clinical order, we will know who the provider is in the EHR, and then we'll have to look up that provider on our side to know who their user is. So once the CCE is assigned to the patient, we basically wait for the battery workflow to get triggered for that patient, which starts when the patient begins the test on the iPad and ends when the results have been generated and uploaded. Once the battery workflow is complete, we'll get a signal, and that is when we can move on to the next step of the integration workflow, which is to upload the results of the core cognitive evaluation to the patient's chart in the EHR. This child workflow that involves importing the patient, assigning the battery, uploading the results, it's also meant to act as a separate service that can be called by multiple different parent workflows. Our integration team is starting to see a common pattern where the parent workflows or triggers are different based on not only our customer environments, but also their vendor capabilities. But the underlying service that encapsulates this child workflow mostly remains the same in terms of design and structure. So some of the things we learned from the POCs were the developer tools are pretty nice. There are readily available Docker Compose files and also the all-in-one binary plus CLI tools. We also determined that with Temporal, there is definitely a lot less orchestration code that we have to write compared to our in-house solution. We also learned that we can prevent ongoing workflows from being affected when we deploy changes to the workflow code. We also learned that we can use temporal signals to pause or trigger custom logic in workflows. Retries of workflows seem to be infinite depending on how you configure it. And in the case of the integration space, we can sleep and resume workflows and also implement infinite polling. We can also fan out events with child workflows and fan in events with conditions and signals. And then also we found out that OTel was supported as an interceptor. So at this point, we had made the decision to officially use Temporal, but the main concern we had was figuring out how to manage the Temporal server as we scaled our workflows over time. We already knew that we had to self-host our workers, but we had originally assumed that we were going to provision and manage the temporal server and persistence layer on our own. And then we started thinking about what the trade-offs were for resourcing. And that is when we started looking into Temporal Cloud. So we created an internal business case for using Temporal Cloud by basically comparing it to OSS Temporal. Infrastructure management was a big one. Temporal Cloud obfuscates the provisioning, maintenance, and upgrades associated with the temporal cluster and database. And because we are an ECS Fargate shop, we also knew that if we were to go with OSS Temporal, we had to spend time deconstructing the available Helm charts into ECS concepts or just relying on the CDK constructs that were published by someone in the community. And that would just take some engineering time away from our core business products. Data encryption is critical to us because we are a healthcare company and therefore deal with a lot of PHI. And we found that Temporal offers a general purpose data converter SDK that we could also customize and plug our own encryption keys into. And we learned that we could use this easily with communications with Temporal Cloud. Local development kind of looked the same between Temporal Cloud and self-hosted because of all the Docker files and Docker Compose and the CLI tooling that was already available. Support, however, was a huge factor for us leaning towards Temporal Cloud because if we were to manage Temporal on our own, we technically wouldn't really have official vendor support, and it would just be more difficult because, again, we're not a Kubernetes shop. Temporal Cloud support also comes with unlimited free design and code reviews, so that was a bonus for us, especially since we were basically new to the technology, so we knew that a lot of engineers would have to account for some ramp-up time. We also analyzed the total cost of ownership and used the battery workflow and clinical orders workflow that I just described as examples when estimating monthly and yearly pricing. So for Temporal Cloud, we estimated the number of actions per month based on how the workflows were designed and also the projected number of customer activity over time. For the self-hosted option, we determined monthly costs of running the infrastructure ourselves and then also the opportunity costs with our engineers. Because again, since we're an ECS shop, standing up a temporal cluster would have strained our resources when it comes to reverse engineering the Kubernetes recommendations into ECS, as well as taking into account maintenance and internal support over time. So we ended up signing up for a Temporal Cloud subscription and began a phasing plan. We're going to start implementing temporal workflows and workers in our lower environments first, specifically our dev and QA environments. We're going to create namespaces tied to dev and QA, with each namespace representing a combination of region and environment. And just as an FYI, we currently support 3 regions per environment, but learned that there's not really a hard limit on the number of namespaces you can have in Temporal Cloud. And I think namespaces are still tied to regions specifically for Temporal Cloud. We also need to provision certificates to connect to our cloud namespaces. AWS Private Certificate Authority is pretty expensive, and given that we're trying to just implement this in our lower environments for now, we're just going to use TCLD to provision and upload those certificates. These certificates will be used to establish communication between our self-hosted workers and Temporal Cloud. The longer-term plan is to establish temporal workers that are owned by teams, and we'll start implementing our, V2 battery workflow and clinical order workflow first, which are owned by our platform engineering and integration engineering teams, respectively. We also have a requirement to make sure that any data that is sent to Temporal Cloud must be encrypted. So we'll create our own implementation of the data converter and integrate it with KMS and publish that as a common package to be used by all our workers. And since we want to be able to use the Temporal Cloud web console and view the data we are sending and help with debugging, we'll need to stand up a codex server that uses the data converter that I just mentioned for remotely encoding and decoding payloads. We also want to secure the decode endpoint of the codex server by having Temporal send us JSON web tokens, and this seemed to be easily configurable with Temporal Cloud. As for observability, we currently use Datadog, and we want to be able to publish metrics to Datadog. Temporal Cloud already provides a Prometheus endpoint that we can scrape data from and forward to Datadog. So in terms of our immediate next steps, if it's not obvious already, like we're not actively using Temporal Cloud yet. So we're going to create worker and workflow templates to be used by our engineering teams. Those templates will serve as a basis for implementing the new processing pipeline / battery workflow, as well as the integration orders workflow. We're also going to stand up a codex server with an endpoint, as well as worker clusters. And we're going to create a shared package for the data converter and encryption and decryption. So probably going to publish like an NPM package to Code Artifact. And once we get this running in our lower environments, we'll start doing some cost analysis based on our namespace usage and then determine optimization approaches from there. So in summary, some of our key takeaways included easier deployments. So with adopting Temporal, we can reduce the amount of distributed single-purpose queues and Lambda functions we previously used to support our workflows, which means there are a lot less external pieces to worry about when deploying new workflows and features. Another one is that Temporal gives us better visibility into our workflows and also makes it easier to test our workflows. Because our old / current workflow architecture had so many distributed queues and Lambdas that also had a bunch of circular dependencies, also exacerbated the fact that we did not have a standardized event sourcing pattern in place. Being able to reliably test some of our workflows was very difficult. And when it came to production issues, debugging could become a bit of a nightmare for our engineers. We concluded that Temporal can help us ensure that our workflows are more resilient because it also guarantees idempotence through event sourcing, detecting duplicate retries or activity commands, and then also maintaining event histories, which is huge. And as for scalability, this is more tied to our business as we grow. Temporal will allow our engineers to focus more on enhancing and building out products used by our customers rather than worrying about the stability of our platform and continuously patching the architectural issues that they keep finding. And that is it.